All right, today we're going to go on a little journey. We're going to start with one absolutely spectacular galaxy, and we're going to end up with a huge and, pretty controversial idea about the invisible forces that shape our entire universe. So let's just dive right in. Our story starts pretty far from home. We're talking 33 million light years away. I mean, just try to wrap your head around that number for a second. That's the incredible distance to the object at the very heart of our mystery today. A whole island of stars and gas and dust, whose beautiful shape is holding a really deep secret.
So, let's meet our main character. We're heading out to the constellation of Leo, to a galaxy that astronomers know as Messier 95, or just M95 for short. Now, M95 is what you'd call a classic barred spiral galaxy. And it's not flying solo out there. It's part of a whole cosmic neighborhood called the M96 group, hanging out with over 20 other galaxies. But what makes it so amazing to look at are its features. You've got this really clear bar of stars slicing right through the middle, a super bright center just cranking out new stars, and this gorgeous ring wrapped around it. It is a very busy, very active place. But here's the thing. When you or I look at a picture of M95, we're really only seeing half the story. All those stars and all that gas we can see, it's all draped over an invisible structure, like a kind of cosmic scaffolding. You could almost call it a magnetic skeleton.
That's right. For the longest time, the thinking was that gravity was the only big player when it comes to sculpting galaxies. But we know now that they're threaded through with these enormous, powerful magnetic fields. And these fields aren't just sitting there, they're actively shaping the galaxy, guiding gas, influencing where stars are born. They give galaxies like M95 their basic shape. But realizing this opens up a huge and surprisingly tricky question.
And that question is a really big one. Where in the world do these gigantic magnetic fields actually come from? The answer, well, it's a little fuzzy.
Okay, so the standard story for smaller magnetic fields, like the one we have here on Earth, is something called a dynamo. The idea is basically that churning molten metal in the Earth's core generates the field. But, as this quote from New Scientist points out, when you try to scale that same idea up to an entire galaxy, well, it gets a lot harder to explain. The physics just doesn't seem to stretch that far. And let's be honest for a second. Turbulent mixing of conducting fluids is a pretty vague phrase, isn't it? Does it really describe a physical cause, or is it more of a placeholder for a process we just don't fully get yet? It kind of leaves you wondering if there's a more direct, a more fundamental answer we might be missing here. And look, this isn't just some fringe critique. As the astronomer Brian McNamara says right here, this is a known puzzle inside the scientific community. We can see the magnetic fields, we can measure what they're doing, but explaining where they came from in the first place, especially on the scale of a whole galaxy, that's been a tough nut to crack. So, let's check out a different kind of answer, one that goes back to the absolute basics of physics, to something we figured out almost 200 years ago, an answer that's all about currents. Okay, this is the absolute key, right here. Way back in 1821, Hans Christian Ørsted discovered a basic law of our universe. An electric current will always create a magnetic field. It's a one-to-one relationship. That means wherever you find a magnetic field out there in space, there has to be an electric current causing it. Why? Because as the physicist Donald Scott puts it so well, there are no bar magnets in space. The magnetism has to come from flowing electricity. This forces us to completely change how we even talk about these fields. You often hear phrases like magnetic fields being draped over a galaxy or delivered in bundles. But that paints a really misleading picture. Magnetic fields don't just exist on their own. They are an effect. The cause, the thing that's actually doing the work, is always an electric current. And what's so powerful about looking at the cosmos through this electric current lens is that it suddenly helps explain things that are otherwise really puzzling. Take a solar flare, for example. The magnetic fields only model has a hard time explaining that sudden, incredible burst of energy. But if you think of it as a massive short circuit in a plasma circuit, the explosion makes total sense. Same with those beautiful thin filaments we see in the sun's corona. They look a lot less like static magnetic tubes and a lot more like the visible pathways of flowing electricity. So, to really get a feel for how this might work, let's use a great analogy and zoom in on our own star for a minute. Let's start thinking about the sun as a giant cosmic electrical transformer. The basic idea behind a transformer is really simple. A changing electric current in one wire coil can actually create or induce a totally new current in a second coil, even if they aren't touching. And that new secondary current, it then produces its own magnetic field.
This transformer action is a way to generate new currents and magnetic fields out of thin air, so to speak.
And this picture shows the basic idea perfectly. You have an electric current, that's the wire wrapped around the core. And that current generates a magnetic field, or flux. Those are the arrows flowing through the core. It's a direct cause and effect relationship. Current goes in, magnetism comes out. It's as simple as that.
Okay, so now let's apply that simple concept to our sun using this diagram. In this model, we imagine a main electric current flowing up along the sun's axis. As that main current changes, it induces secondary currents that start swirling around just below the sun's surface. And what do those brand new currents do? You guessed it. They generate their own magnetic fields, which then burst out from the surface as the magnetic loops that we can actually see. And here's the real kicker. This isn't just some neat idea. It offers a potential physical explanation for a very real, very old solar mystery, the 11-year sunspot cycle, where the sun's entire magnetic field literally flips upside down. The physics of transformer action shows exactly how a changing primary current could cause a secondary magnetic field to reverse its direction. It actually fits what we observe. So, armed with this whole new way of looking at things, let's zoom all the way back out and finish our journey where we started.
So what does our little solar transformer have to do with that beautiful barred spiral galaxy M95, 33 million light-years from here? Well, the logic is scalable. If this principle of electric currents creating magnetic structures works for a single star, could the very same fundamental physics be at play shaping an entire galaxy? And this brings us to our final, and yeah, pretty mind-bending question. What if that magnetic skeleton of M95, and of all galaxies, isn't just a skeleton at all? What if it's the visible effect of a vast, galaxy-spanning electrical circuit? It suggests that maybe, to really understand the cosmos, we need to see it not just as a place of gravity and matter, but as a dynamic and fundamentally electrical universe.